Hello, everyone. Welcome for joining us today. Our webinar entitled Real-Time Video Surveillance and Anomaly Detection. My name is Yasin Hariri. I am Senior Staff Scientist AI and ML. And this webinar and reference design are supported under Fabric Innovation Platform. So I'm just going to give you a high-level overview about our webinar today. We have a lot of content, so let's keep going. So the first thing is a high-level overview about Fabric program that is led by CMC. Then we will dive into the topic today, which is Edge AI for video surveillance. But before that, we will introduce our products and services for Edge AI solution development. Microscan and application roadmap at CMC Microsystems for 2024. Then we will explore how Edge AI is transforming video surveillance with leading-edge technologies and tools used to implement application in that space. Our use case today is well-defined, and the objective is enhancing workplace safety through real-time anomaly detection of safety gear compliance. So we will build the application that aims to enhance workplace safety by monitoring these compliances. And we are going to use a leading-edge innovative model, YOLO v9, to implement our application, followed by a live demonstration that will walk you through the process from training the model on your custom dataset to the deployment on a server class GPU to the optimization for an Edge AI platform, in our case today, the Jetson Orin Nano. And we will conclude by a Q&A session. So what is Fabric? Fabric, funded by ICED-SIF and led by CMC Microsystems, aim to foster a vibrant, sustainable Canadian semiconductor ecosystem. So we support companies developing made in Canada semiconductor technologies, fostering industry collaboration, and promoting Canada's role in the global supply chain. Sorry. So the challenges. There are challenge projects that support Canadian industry and academia in developing next generation made in Canada semiconductor processes and products, and fabrication process development focus on key technologies including photonics, compound semiconductor, MEMS, and quantum technologies. The IoT projects focus on advanced sensor, semiconductor innovation in key sectors like clean health, healthcare, telecom. So the design tools and method and prototyping fabrication to accelerate the adoption across Canada semiconductor ecosystem. So what we offer up to 50% reimbursement for industry and 100% for academic on eligible cost. And these challenges enhance semiconductor manufacturing and expand Canada fabrication capabilities and grow the critical supply chain. The Fabric Innovation Platform, where we are offering this webinar and reference design under it, offers tools, technical resources, and training to build a sustainable talent pipeline and accelerates product development and support world-class research. There's a list of upcoming training. We delivered yesterday a Swift Mode webinar, and today we're delivering this one. But stay tuned for the COMSOL multiphysics training, which will happen on October 15-18, and quantum superconducting quantum device training on November 18-22. We have a number of ecosystem events planned to bring all players together from across Canada. And one of the most important one is the Canadian Semiconductor Symposium, which take place on October 9-10 on Markham, Ontario. So becoming member. So the ecosystem is open to organizations and individuals in Canada, including professionals, academics, government, and industry experts with interest in the sector. And through Fabric, academics and their students will continue to enjoy the benefit of their CMC academic subscriptions, including CAD, tools, fabrication services, Basecamp, They also have access to other services and training offered to Fabric ecosystem members. So why CMC? As you know, if you are familiar with CMC, we have over 40 years history of supporting research and the introduction of advanced technologies in Canada. And one example is the CFI MSI, which aims to build Canada's national design network. So CMC was selected for running the Fabric program for its great reputation and strong network across Canada. Now, this section will explore CMC offering in the space of Edge AI. So this is an overview of our one-stop shop for Edge AI development, which take you from the concept to prototype. We start by defining the problem, setting goals, and addressing hardware and software constraints. Next is the data management for collecting, labeling, and augmenting the data. Then we move to model training, where we select, train, and validate models. After that, we focus on model optimization, making models faster and more efficient through quantization and pruning. And finally, once the model is optimized, we handle inference and deployment, ensuring smooth integration on edge devices for real-world applications. We have built an advanced infrastructure to do this. And the main objective here is to effortlessly train, optimize, and deploy machine learning models on edge devices. So on the cloud side, we have a FPGA GPU cluster, which allow training large model. And we are going to use the GPU cluster today to train our YOLO V9, which is the heart of our application. We support a wide range of frameworks to perform training, optimization. For example, today we are using PyTorch as a training framework and TensorRT to optimize our model. On the inference side, we have partnered with leading edge companies in Canada, including Tether AI and TensorRT, who have built a custom AI accelerators that are specifically designed to support inference workloads. We have also built an ecosystem around RISC-V. We have mature RISC-V cores and platforms that allow you to benefit from the open source, open hardware group cores and implement your own implementation for your own product. We support off-the-shelf platforms such as the Jetson Orin, which will be used today to demonstrate the capabilities of Edge AI in video surveillance. So do not hesitate to request access to this platform, and you will get not only the access, but full support to implement your own project. Our IoT team offer IoT customizable sensor platform. This one is the Swift mode, where the webinar yesterday was about. And it is an open PCB, customizable, so you can download it from CMC Microsystems and customize it for your own application. It supports a wide range of applications, including Bluetooth Low Energy Wireless Mode for sensor network R&D, low power sensing. So if you have a sensor that you would like to integrate and test, this is a suitable platform for that. It supports sensor fusion, machine monitoring, and electromechanical sensing. And we have a team of experts at CMC that support you through the journey of adopting and using this platform in your real application. Join the group. We have a LinkedIn group, companies, startups, individuals that are experts in the machine learning and AI space in Canada. So you can join this group to get the latest news, events, and access to advanced reference design from CMC Microsystems. Just a quick overview about the Edge AI Microscan in 2024. So as you know, multimodal generative AI has emerged as a major trend, and it has a very important impact on the economic scale. Generative AI poised to automate 60 to 70% of the work, and 60% favor multimodal AI by 2026, which require a lot of performance on both cloud and edge. Bigger LLMs diminishing returns. People are trying to optimize bigger LLMs, especially for edge, because they need to run at very low power budget. Edge AI transformation, which consists of the migration of AI workload from the cloud to the edge. Another great example, a lot of video analytics were implemented in the cloud using big servers. Now, moving a lot of this analytic close to the sensors offer various advantages, including low latency, bandwidth saving, data privacy, security, and autonomy. This has led to a critical need for energy-centric AI hardware which balance performance and power. Since 90% of the power is consumed by data movement, especially for large LLMs, new architecture emerged to deal with this issue, to minimize data movement on chip, including at-memory spatial architecture for low-power scalability, domain-specific neural processor, complex memory hierarchy, and massive parallelism. So there's a lot of innovation on the hardware side to deal with the increasing complexity of these models. And efficient ML mapping tools, because you need to reduce the time to market. So you need efficient ML mapping tools that provide you with the highest level performance possible at a very short time. Without forgetting that there are some progress in non-conventional architecture, such as quantum, spiking neural network, and analog computing. So this is our application roadmap. And the main objective here is to showcase advanced AI ML capabilities at the edge, complement the IoT projects by adding real-time analytics and intelligent decision-making. We are aligning with Fabric's AI technology roadmap. And for each of these deliverables, we will provide methodologies for training inference, trained models, application code, and video demos. Today, we are delivering real-time video surveillance and anomaly detection with a complete methodology for training and inference, but also the application code that will help you run the application and customize it for your own objective or your own problem. Under development is the Edge AI-based generative AI, which will demonstrate using generative AI on Edge. The third one is autonomous vehicle fleet management. The fourth one is remote health monitoring system with AI integration. Fifth one, predictive maintenance for manufacturing equipment. And last but not least is smart crop monitoring and management. So the objective of this Edge AI demo is to demonstrate AI capabilities at the edge. So stay tuned, because for each of these one we will provide not only the reference design and how it works, but also a complete webinar and support for those. Now the topic today, transforming video surveillance and the power of Edge AI. So Edge AI represents a shift in how we handle video surveillance by processing data locally rather than relying on the cloud. And this transition not only speed up response time, but also conserve bandwidth, which is crucial as the volume of data continues to rise. So the growing interest in Edge AI technologies reflects a broader trend toward more efficient intelligence video analytics. Edge AI and video analytics work hand in hand to automate tasks traditionally performed by humans, such as analyzing foot traffic in retail environments. By moving processing capabilities close to the data source, we can achieve quicker, high, and more efficient monitoring. So this integration is pivotal for security application, where immediate alerts can make significant difference. And as organizations increasingly become data-driven, the complexities of managing data from numerous endpoints grow, and Edge AI address these challenges by providing real-time analytics and reducing latency issues. So analysts predict a significant increase in video analytics application by moving to the edge and highlighting the technology's transformative potential. So the future of surveillance and analytics will see more intelligent systems that enhance security and operational efficiency across various sectors. Here is an example of some Edge AI application that is used And for each one, we have an envelope of how much performance we need. So facial detection, human activity recognition, this usually run on your cell phone and require less than 1 TOPS. And the second class, require 1 to 50 TOPS. They are more like use heavier model in augmented reality, surveillance, digital still cameras, facial recognition. To more power-hungry, power-efficient applications such as autonomous cars, ADAS, high-end surveillance, next-generation gaming, and next-generation augmented reality. So for each class of application, you need a specific class of models which require a specific performance envelope. So in terms of the key technologies and tools, today we are using the Jetson Orin Nano. And it features an architecture equipped with the NVIDIA Ampere architecture, GPU, and it includes up to 8 streaming multiprocessors, totaling 1,024 cores, and 32 tensor cores dedicated to AI processing. So a lot of machine learning application will run on those tensor cores. So it's a capable platform, and it's very good to start with. It has CSI port to handle frames coming from a CSI camera for very low latency. It has also GPIUs to handle sensor data or other type of input than video, and also the usual ports that are very important for debugging, such as USBs and Ethernet and video output to display frames coming from your platform. NVIDIA shipped with this platform a complete software stack for development, the Jetson Jetpack. It's a complete software stack that allow you to deploy models across various architecture, various framework, TensorFlow, PyTorch, Caffe. But the most important thing is the Jetson Linux security and the runtime, which that allow you to run efficiently application on the GPU. It has also some platform services to integrate with the cloud, such as AI analytics and other libraries and services that you will explore. In our case, we are going to use a standalone version. And the GTOP here show you the architecture or the cores that are used in the Jetson Nano. In this case, we have 6 cores. It provides you with the workload of each, the usage of the memory, and the usage of the GPU. On the information side, you will see the latest, what is installed in your Jetson Nano, the CUDA version, CUDA neural network version, TensorRT. All these are important information that allow you to see if your current setup is compatible with current application. Otherwise, you need to revise the software stack. So one of the most important thing here is TensorRT. It's a tool that is provided by NVIDIA that allow you to optimize models that are trained in a data center GPU to a small device like this one. So it significantly enhanced performance by accelerating inference speed and reducing latency, which is essential for real-time AI application. It also optimized memory usage, enabling more complex models to operate efficiently on this powerful yet resource-constrained device. With support of ONNX, deploying pre-trained models is straightforward, as you will see in the demonstration today, making TensorRT a vital tool for real-time video processing. So our use case today. Our use case is very clear. We are aiming to enhance workplace safety through real-time anomaly detection of safety gear compliance. The key anomalies that we are planning to detect are the absence of boots, ear protection, glass, glove, helmet, mask, and vest. So since the YOLO v9 is trained on a COCO dataset, which is 82 classes of various objects, and since we are interested only in these objects, we need to fine-tune the model. We need to retrain the model on this dataset. So the first thing is to find the dataset, retrain the model, and see if the model can detect these classes. This is what we are trying to implement. Our Edge AI development flow is as follows. So we are going to start with the pre-trained model. We are going to test it first. Before we do anything else, we need to test the model if it's working and the application if it's working. So we're going to test it on a TESLA v100. Then we're going to retrain the model on our custom dataset that support these classes. So each class will have a number of images. We retrain the model and fine-tune it and see if it performs well, if the detection is high. We are going to test the model again on the TESLA v100 with post-training benchmark and evaluation, the performance evaluation. Once we are satisfied with the performance of the model, we're going to switch to the small device, which is our case Jetson Orin Nano, for real-time detection. Since it's a heavy model, we are not expecting that the model will perform well. Then we need something like TensorRT to reduce the size of the model and optimize it for real-time inference. And this is our main goal. It needs to run at a very nice FPS to be suitable for deployment. Since we are using YOLO, this is a brief introduction about YOLO. I'm not going to dive into any details, but the main objective is identify and locate objects in images and video frames, as you know. So we want to recognize the presence of objects and draw precise boundaries around these objects. And this has many applications in video surveillance, autonomous vehicles. You can detect pedestrians, in healthcare diagnostic, you can diagnose some parts of the image that contain, for example, tumors, retail analytics by counting people in and out of the stores, enhancing workplace safety, which is our demo today. And the impact is to transform machine perception and interaction with visual world, which is a mature field right now. As you see, every year we have a version of YOLO coming out. We implemented YOLO v9, but the framework, the methodology work well with YOLO v10 as well. So YOLO v9 was released by a team led by Chanya Wang. You can Google this up, and you will find their repository and their paper. But at high level, it introduced significant improvement to the YOLO model series. One of the standout features is to focus on resolving the information bottleneck problem that previous version overlooked. So while traditional deep learning networks face challenges like vanishing and exploding gradients, YOLO v9 employs techniques such as batch normalization and more effective activation function to enhance the performance. And these advancements contribute to better detection capabilities, making YOLO v9 a powerful tool in the field of computer vision. So the components, YOLO v9 are recognized as the most widely used object detectors in the computer vision. YOLO v9 paper built up upon YOLO v7 and proposing several advancements. It introduced 4 crucial concepts: the PGI, or programmable gradient information, generalized efficient layer aggregation, and the information bottleneck principle, and the reversible function, and they all aimed at improving the performance. Currently, YOLO v9 excels in various tasks, including object detection, segmentation, and classification. It has 4 variants, and each variant varying parameter count to cater to different applications. So the author, in order to address the challenge of the information loss in neural network, particularly in complex architectures such as YOLO-v9, such as YOLO-v7 and YOLO-v8, YOLO-v9 introduced a new concept which is called the reversible function at the right here. And while increasing the number of parameters can enhance a model's capability, it often leads to overfitting. So the reversible architectures allow the network to retain original information at each layer, ensuring operations can revert input to their initial state. This equation explain this concept. So the input is X, and as the inputs go through different layers, you have more probability to lose information through these transformations. So the information bottleneck concept highlights the challenge of losing vital information as the network gets deeper. And the PGI deal with this issue by reducing this information loss. And since the framework is the PGI is considered as a novel approach introduced in YOLO-v9. You can read the paper to get more information. And the most important objective is to enhance the gradient supervision. It consists of three components: the main branch, which handle the inference process efficiently without incurring additional cost; an auxiliary reversible branch that helps overcome challenges posed by deeper networks, and thus addressing information bottleneck and ensuring reliable gradients; and multi-level auxiliary information, which is particularly useful for managing error accumulation in models with multiple prediction branch. Overall, this framework provides a structured way to improve learning outcome in deep architecture. And for a deeper understanding of each branch and its application, I encourage you to refer to the research paper. In terms of performance, YOLO-v9 advantages. So compared to YOLO-v7, YOLO-v9 has 42% fewer parameters and 22% less computation, achieving the same AP53. And compared to YOLO-v8, YOLO-v9 shows 16% fewer parameters with over 20% or 27% less computation. So it performed well while detecting more objects accurately. Now the live demo. Before we dive into the live demo, I would like to go through some key elements of the live demo. So as I mentioned before, we retrained the model. The first thing here is we use the training script provided by the author of the paper directly, and this approach works perfectly. And we use the custom data set. I'm just going to switch to pointer. So we use a custom data set, which is dataset work safety, and which has all the classes. And we use ClearML for tracking and visualizing the YOLO process, and TensorBoard for the visualization. So this is the result of the training. And as you see here, the performance metrics for our test set, 32 images and 1,514 instances, show overall precision of 93% and recall of 91%, resulting in a mean average precision of 96%, which is high and which is acceptable. We also have the performance for each class. So for example, if you retrain the model for your own data set and you discover that one of the class doesn't perform well, it will guide you through the process on how to increase the accuracy of that class, either by adding more data set to that class because it's underrepresented, or by balancing with the other classes. But most of the classes perform well. And as we will see in the application, maybe one or two classes are underrepresented, but I will show you in the demo how to detect them, how to identify them. In terms of the training on custom dataset, the most important metric to track often depends on your specific objective, but generally this one is crucial for evaluating the model. So it's the mean average precision, and it's a comprehensive measure of how well the model detects objects across different classes and is sensitive to both precision and recall. So we have a model that performs well, and we can test it on our edge device. This table summarizes all the demo process. So the first line here, this is the inference of the original model on our Tesla V100 on our GPU class, server class GPU. We achieved 52 FPS frame per second. We have also tested the framework on a workstation GPU, the RTX A4000. We achieved 76%. Although it's a smaller GPU, it's performed better. I did not investigate why a smaller GPU on a workstation class outperform a server GPU, but I think because the A4000 is a newer GPU and therefore it has some hardware capabilities that are suitable for inference compared to the V100, which is a monster in training a neural network. Now things get serious when we fine-tune the model. This is custom inference. As you see, it's similar to before. But when you go to Jetson Orin without any optimization, the frame rate or the FPS drop from 70 to only 11. This explains why we need optimization at the edge. It's not easy to bring a large model that is trained on a cloud GPU to a small GPU. You're going to waste a lot of performance, and therefore it's not even practical. So optimizing the model using TensorRT allowed us to run at 30 frames per second, and therefore we are in the standard range of deploying this model for video surveillance. So let's go and check the demo. So we didn't post yet the reference design, but it's going to be available here by tomorrow or by the end of the week. But you can take note of this repository. It will have the script, the dataset, and everything. It's on this website. It's fabricinnovation.ca RTVSAD, real-time video surveillance and anomaly detection. So I let you take note of this, and then I will unshare my screen, and I will share with you the screen of the demo. Okay, so I'll close this screen, stop sharing, and I will share another screen that has the demo. It starts with this one. All right. Okay, so the first thing we're gonna do, we are connected to our GPU cluster. This is where we train the model on the Tesla V100. So I'm not gonna run the training again. I'm gonna just show you how it progressed. So here, the command that we have run is as follows. Is the one I showed in the presentation. I'm trying to find it. So we used the training script, train the all, on our GPU. Here we have which GPU we are using. It's a Tesla V100. Here it prints some of the components of the model, and then you can look at the training as it progresses. and at the end it will show you the results. So instead of looking at the results here, I think it's prettier to look at this on my VS Code environment. So this is the VS Code environment, the RTX GPU. So the structure of the directory, here we have the different data sets for training, validation, and test. So if you look at the images, they are all images of in workers in environments, and the labels will show you the boxes of each object, and this will be used for training. But let's look at the result. This is the result I have showed. So when you finish the training, the result will appear in the latest directory. For example, in this case, in the training directory, you will have the weight. This is the weight of the new model, the fine-tuned one. And you look at the results. For example, the confusion matrix is also interesting because it shows you how we are doing for each class. In some classes, we don't have very good results because they are underrepresented. You can look at other files. For example, here's the parameter files. In this one, it shows you the labels that are used. As you see here, we have the air protection, the glass, and the gloves. They are underrepresented because we don't have a lot of data for this. And this is why they are not performing well. But for boots, helmet, person, and vest, we achieved very good results because we have a lot of data for those ones. And of course, the last one, the results show you the most important results. This is where you will see if your model perform well or no. Now, as for the demo, what I'm going to show, the first thing, we're going to run our original detection script on different video files. So I'm just going to post some commands here. There I launch on the original models, which is the one we downloaded. As you see here, we don't detect any protection gear because this is the original model. It just detects the classes that are in the COCO dataset. So workers are individuals, and we display at the end the inference time and how much time we spent in pre-processing and in post-processing. You can test it on different files to see how it performs. But overall, it does the job that is detecting objects. Here we just detect individuals in a working environment. And I have some other video files here in a real environment like traffic environment. We can see that it detects cars, traffic lights, and other classes that the model was trained for. Motorcycle, people, traffic lights. So this is the original model. I encourage you to test the original model before you do any optimization or any retraining. Now we trained the model, and now we have a resulting file, which is our new weights. So here we are running a new script underscore PPE because we need to modify the original script to fit with the new datasets. And the weight, we are not using the original model, we are using BEST. This is the model that was obtained by fine-tuning the original one. So this is supposed to detect all the protective equipment we are trying to detect, such as helmet, vest, boots. So as you see, we are interested to those. So for each individual, we can detect if the individual is wearing these protective equipment. So this means that the fine-tuned model works. Now the next step is to go on the Jetson. So for that, I'm going to switch to another window where I'm connected to the Jetson Nano Orin. So I have a no machine session to it. I'm just going to run some demo here. The first one you would like to run is executing the detection script of the fine-tuned model. So let me find the command. So this is the command for that we just run. I'm going to pass it here. So the same script that I just run on the workstation, I run it with the same weight that I obtained from fine-tuning, but now it's for Jetson on the Jetson Nano. As you see, it's going to take forever to execute, resulting in 10 frames per second, which is pretty low. So as you see here, it's performing really slow. It's 10 frames per second, missing a lot of information. It's still working, but it's not suitable for real-time application at the edge. Since I'm processing 400 frames, I'm just going to keep this running and grab the command that used the latest script. So now what you want to do is to optimize this model for the Jetson Nano Orin. We are going to use TensorRT. So the first thing we need to convert. I'm not going to run these commands because they take forever. I'm just going to explain them. So this one exports the best.pt to an Orinix version of it. This allows you to run the Orinix version on Jetson Nano or on any other platform. So I have the Orinix already generated, but the most important one is this one. So this one translates the Orinix model, results from the previous command, to a new file, which is the engine, the best.engine. The best on the .engine is the optimized version of our model. And this is the one that we obtained 30 frames per second. So let's just run it. It explicitly used the weight. So this script will load the engine models and we'll run it on the same file. But as you see here, it's pretty fast. We changed the resolution just to show how it's working, but we are working at 30 frames per second on Jetson Nano. So this concludes the demo. And now we are going to give you an opportunity to ask questions. We still have 10 minutes. Thank you very much for attending our webinar today. Have a nice day.